Hello, everyone. Welcome to this IEEE ICASSP 2021 tutorial T12 titled Underdetermined Wideband Direction of Arrival Estimation and Target Localization. My name is Wei Liu. I'm from this Communications Research Group, Department of Electronic and Electrical Engineering, University of Sheffield, and the UK. And here's my email address and my website, so you can know more about my research from this website. First is the outline. So it's introduction to wideband array signal processing first, basically highlighting the difference between narrowband and wideband array signal processing in terms of both beamforming and direction arrival estimation. And then I will give you a review of sparsity-based underdetermined narrowband DOA estimation methods, which will form the basis for the wideband case. And then I focus on this underdetermined wideband DOA estimation method with direct group sparsity. So basically apply or extend this narrowband approach to the wideband case directly using this group sparsity concept through this frequency decomposition. And then this section 4 is underdetermined wideband DOA estimation exploiting frequency diversity. So for underdetermined DOA estimation, normally we assume we will use a sparse array, but actually for wideband case, a sparse array is not really necessary for underdetermined DOA estimation. So you can still use a traditional uniform linear array to do underdetermined wideband DOA estimation. So we'll talk about this part in this section 4. And then section 5, we talk about underdetermined wideband DOA estimation exploiting higher order statistics. So basically, we can increase the degrees of freedom of the system by exploiting these higher order statistics like cumulants. And then section 6 is underdetermined target localization based on wideband arrays. So traditionally for target localization based on DOA estimation, you have multiple subarrays, and then each one will estimate the direction of the target. And then with the direction information, then you can find the location of the target. That's a two-step approach. But in this part, I will talk about a one-step approach. Basically, we estimate the location of the target directly. Okay, it's not two steps. We find the location directly using, again, this group sparsity approach. Then finally is a summary. And this whole tutorial, there will be 3 parts, this recording. So section 1, section 2 will be the first part, 3 and 4, the second part, and 5, 6, 7, the third part. Okay. First is section 1, so introduction to wideband array signal processing. And then 1.1 is introduction to array model, and then we talk about the difference between narrowband and wideband in these 2 aspects. So one is beamforming, one is DOA estimation. So array model. So here, so array signal processing involves multiple sensors placed at different positions in space to process the received signals arriving from different directions. And it has a wide range of applications, including radar, sonar, microphone arrays, radio astronomy, seismology, medical diagnosis and treatment like ultrasound array, and wireless communications. So here you have multiple sensors in different spatial locations, have multiple signals coming. Certainly this case is for the reception mode, and we can also use this array system for signal transmission, not just the reception. And we normally assume the array sensors have the same characteristics, and they are omnidirectional or isotropic. So that is, its response is to an impinging signal is independent of these arriving angles. So according to According to relative locations of the sensors, arrays can be divided into one-dimensional arrays or linear arrays, two-dimensional arrays or planar arrays, and 3D arrays or volumetric arrays. And each of them can be further divided into two categories, like a regular spacing, including both uniform and non-uniform spacings, or irregular or random spacing. And according to the construction of individual sensors, so we have traditional scalar sensor arrays. So basically, most of the research is based on this kind of array. And then we have vector sensor arrays, and there are more and more research activities in this area. And examples for the later for this vector sensor array is, like this cross dipole or triple arrays. There's also spatially stretched triple array, and so on. All kinds of variations of this dipole-based system. And then we also have this acoustic vector sensor array. Okay, there are different sensor arrays. We can classify them into different categories based on different criteria. And for array signal processing, there are three major research areas. One is, we detect the presence of impinging signals and determine the number of signals, how many signals are coming. And also we estimate the DOA angles of impinging signals, so where they come from, basically. And then there's beamforming, so enhance the signal of interest from some known, unknown directions and suppress the interference signals simultaneously. Okay, so basically three areas of research. And depending on the bandwidth of the signal, we could have a narrowband system or a wideband system. And although this tutorial is focused on the wideband case, since many narrowband methods can be extended to the wideband one, so we will start from the narrowband case first. And here is a general array structure. It's using linear array as an example. So like linear array, all these sensors, they are positioned along a straight line. And you have a signal coming from directions theta. And this theta is measured from this direction. We call it the broadside of this linear array. And when signal arriving from this theta, you have a delay between different sensors. So here you receive the signal first, and then for this sensor one, you have a delay tau1 and tau2 and so on. So in total, you have big AM sensors here. And we consider a complex plane wave signal ST times e to j omega t arriving from this angle theta. And theta in this case is from -90 degrees to 90 degrees. And ST is a baseband signal, and omega is a carrier frequency, okay, which is much larger than the bandwidth of this ST. Okay, here's ST. And we assume the signal received by the first sensor is just the signal itself. Basically, we're using sensor 0 as the zero phase reference point. And then for sensor M, the received signal will be delayed by this tau m, right? So this delay here, but ST minus tau m, so is roughly equal to ST. Okay. This approximation is valid because of the assumption. So this narrowband assumption, because ST has a narrower bandwidth and changes little during the time delay tau m. So there's a little change to this ST within this delay tau m. So the tau m is very short. So all we can see that roughly the condition for that approximation to hold is ST minus tau m is still highly correlated with ST. Okay, if this ST and the ST minus tau m is not highly correlated anymore, then it's not really a narrowband system. So then we have to consider it as a wideband one. Okay. So the condition for a system to be considered as a narrowband or a wideband, okay, is not the relative bandwidth or the baseband signal compared to the carrier or compared to the center frequency. It's really also related to what? Related to the array geometry. if you have a large spacing, so this tau m will be very large, then in that case, you cannot have this approximation anymore. So in that case, it's not narrowband. So you should consider the system as a wideband one. Okay. And in practice, we normally work on the baseband signal instead of at the carrier frequency. So which leads to this following this simplified model. Basically, we remove this e to j omega t. Okay. So we have this baseband model here. And if you have big K signals, SKT, so K from 0 to this big K minus 1. And then we have the widely used narrowband array signal model, right? So we have this SMT equal to this summation, okay, K from 0 to big K minus 1. And this is phase shift, and this is a source signal, the baseband source signal. And we can put all of the received signals in a vector form. So this is the vector. And also this element is phase shift into another, this matrix, and the source signal also into a vector. And here we add this noise. And then we have this xt, this vector, this A, we call it steering matrix. ST is a source vector, and NT is the noise vector. And this steering matrix A, big A, is given by this. You have K steering vectors, this is A omega theta 0, A omega theta 1 until A omega theta sub K minus 1. So, and this is given by this, is called steering vector or response vector. Okay, basically this is A omega theta is just this column vectors. Each column vector is a steering vector for the corresponding source, and is a function of theta. And this model actually is only valid for the narrowband signals, and is not valid for wideband or broadband. Sometimes we call it broadband. Okay. So for wideband signals, the propagation delay between different sensors cannot be expressed in the form of simple complex number, and mathematically a convolution operation is needed. So here is not a simple approximation. Okay, like this delay, the total effective delay is just a complex number, right? Here, complex number. The signal itself, there's no change, ST, across the array. But for wideband case, you cannot have that result. So suppose this SKT, okay, this SKT is original, so K impinging plane wave signals that would be received at the reference point, such as sensor 0. We use sensor 0 as a reference point. We can use that sensor 0 as a reference point or any point in space. And then the signal received at the mth sensor is given by this. So X sub MT equal to this. Here is X, here is XK, okay, not XL, XKT minus tau MK and MT plus this. Okay, this is summation, so K of them. And this tau MK is actually equal to tau M theta K. Okay, so it's here, it's tau M theta K. It denotes the delay from the mth sensor to the reference point for signal SKT. If you use sensor 0 as a reference point, then this tau 0K will be 0. Tau 0K will be the delay between sensor 0 and the sensor 0 itself. So it will be 0. And so matrix form in this time domain, this delay can be represented by a convolution between the ST signal ST itself and this delta function T minus tau MK. So the convolution of this and the signal, the overall effect is a delay. That's the time domain model. And if you look at in the frequency domain, then you have the narrowband model. So for each frequency omega, so frequency domain in the frequency domain for each omega, so you have this without considering this noise. Okay, because we don't for this model, we don't consider this noise here. Okay, just the signal part to simplify the whole notation. So in this frequency domain, we have this narrowband equivalent model. And here is the steering vector for frequency omega, and for the source 0 and source 1 and the source big K minus 1. Okay, that's the frequency domain representation. Okay, and if you go back to this time domain model, if you consider the discrete time case, basically after sampling, so you will have this model, so discrete time model. So in this case, Sn, that's the signal vector at time instant n, and then you have this convolution, so discrete time convolution. Okay, and Sn again, so this is the signal vector at time instant n, and then for this AI, it's not a steering matrix. So this matrix AI, okay, for this matrix AI is M times K, so or M by K matrix AI, and its element, so at its M K position, then is given by this. It's a sinc function basically. Okay, this delay can be represented by this sinc function. Okay, in this discrete form, and T is a sampling period. As an example, so we consider this URA. So basically, I want to give you an expression, more specific expression for this sinc function. Okay, so for URA with uniform linear array with adjacent sensor spacing D, which is alpha times lambda minimum over 2. So lambda minimum is the wavelength corresponding to the highest frequency of the signal, and alpha is the chosen coefficient. And so, but basically you can, if you want to adjust the spacing, then you can change the value of alpha. Okay, and in many cases we choose alpha equal to 1. And for uniform linear array, then tau mk will be equal to m times tau 1k. Okay, tau 1k is as a unit delay for this signal k, and then tau 1k will be d sin theta k over c, right? D sin theta k, that's the path length, okay, and c is the speed of travel for the signal, and m times this, okay, that's the delay. And if we choose a sampling frequency being twice the highest frequency of the signal, then sampling frequency tau will be equal to lambda minimum over 2c. Okay, and then you substitute all this into here, then this AIMK will be equal to this, and this result can be used to generate some similarity data for wideband array signal processing. Okay, because I know from my own experience, some students, they try to when I ask them to generate some wideband data, they don't use this. They try to generate many signals with many different frequencies, add them together. Okay, that's not correct. So you have to use this simulation convolution operation, okay, using this representation to generate the data. That will be the real wideband data model. Okay. Now we talk about the difference. So there are significant differences between wideband and narrowband array signal processing. Okay, so first, for this narrowband case, for narrowband beamforming, okay, the beamformer output YT is given by an instantaneous linear combination of the received spatial samples XMT. So you have the received signals X0T, 1, X1T, X big M minus 1T, and then you basically this multiply them with one single complex number. Okay, we put conjugate here because it's just for convenience when you calculate the covariance matrix. Okay, for to simplify the notations. and you can just put W0 if you like, W0, W1, W m minus 1 instead of this W conjugate m. So this star is conjugate operation. So this is beamformer structure for narrowband. And suppose there are k, so the maximum number of signals. So like suppose we have k equal to m impinging signals from directions of this state k. And the first one is the signal of interest. We want to keep this when we do beamforming. I want to suppress the others. Then in the ideal case, there's no noise. In the ideal case, then this is the coefficient times the steering vector for first signal, steering vector for second signal, and so on. Then for ideal case, perfect beamforming, right, without noise, this coefficient times this, the steering vector of the first signal, it will be 1, and for the other signals will be 0. Then in this case, you have suppressed the interference signals completely, okay? So as long as the matrix on the left is full rank, we can always find a set of array coefficients to cancel the m-1 interference signals. And in this case, so the exact values are dependent on the signal frequency, right? These values will be dependent on the signal frequency. Certainly also the geometry of the array. So given the fixed geometry, then will be depending on the frequency. So since a wideband signal consists of infinite number of different frequency components, the value of the weights should be different for different frequencies, right? Basically, so in the general case, so W omega should be a function. So W should be a function of omega. So how can you, for wideband signals, then this W should be a function of omega. Basically, this W0, W1, Wm-1 will be a function of omega. Then the question is, how can you generate a response, a coefficient W, which is dependent on omega? Okay. What should we do to get this kind of response? Okay, it's very simple. So we can use a so-called type delay line. So it's the analog form, or we're more familiar with is, okay, discrete form. So it's FR filter. So this is delay the sampling period. And then you have FR filter. So this is the coefficient of the filter. Basically, we delay this by different amount and multiply them and then add them together. So that's the standard FR filter. And this filter, you can find the set of coefficients to give you the desired response W omega. So that will be a wideband beamformer. So certainly in this case, this actually this delay can be the sampling period, right? It can be different. So it can be a smaller value or larger value, depending on the applications or the requirement. So that's the wideband beamforming structure. You have a type delay line or FR filter attached to each sensor. Or you can extend this further. So you have this called sensor delay lines for wideband beamforming. In this case, you don't put type delays. Okay, you put extra sensors behind the original sensors. So now there's still delay between the different sensors, right? Between different signals here. This delay is propagation delay, spatial propagation delay. But here is the propagation delay along this line, okay? But it has the same effect, certainly different performance, because here this delay is also depending on the direction of the signal. But here the delay is fixed for different directions of the signal. So this is a sensor delay line based wideband beamforming structure. So in this one, it looks like a narrowband structure because each received signal will be multiplied by one coefficient. So similar to this, but because of the layout of the geometry, so of the array, it's actually, it can do effective wideband beamforming. Or if you have an original planar array, you can put more sensors behind this planar array, then you have this qubit structure. It's still, you can, so with a narrowband structure, narrowband array beamforming structure, but wide, but with additional dimension, spatial dimension, then you can do wideband beamforming. Okay, so we can also consider this as a wideband beamforming structure without temporal filtering, because there's no temporal filtering here, because this one is a temporal filtering operation, right? But here There's only one coefficient, no filtering operation, just multiply this coefficient directly. Okay. Or if the original array is like this, then you put more behind, you have this kind of new structure. Okay, as SDL-based wideband beamforming structure. For this structure, the sensor location optimization is an important problem. So how to find the best layout of the sensors, okay, to give you the best wideband beamforming performance. That's an important issue. That's beamforming. Now for DOA estimation. So for DOA estimation, in the narrowband case, the main idea is to find the unique stream vector associated with each of the impinging signals. And this can be achieved by either beamforming, so we just scan the whole space, such as beam scanning, or the Kaplan beamformer, so it's still a beamforming approach. Or subspace-based method we have been very familiar with, like music, Esprit, or there are many sparsity-based methods. Okay, I just list a few of them because there are many, many others. Okay, and for wideband signals, you can just take one frequency, then that will be narrowband, right? So you can apply all the narrowband methods to solve the problem. However, there are multiple or infinite number of stream vectors associated with each signal. So you have multiple frequencies. You don't just ignore all other frequencies and just take one frequency, right? You are wasting information, right? So the key is how to make use of the information carried by these stream vectors. You have multiple frequencies, not just one single frequency. Then how can you make good use of the information carried by these stream vectors for different frequencies to more effectively identify the DOA of the signal, right? So that's the main issue for wideband DOA estimation. Certainly, we can design a wideband beamformer pointing to different directions, like wideband beam scanning, or draw the output power with respect to direction to find the peaks. That's a classical approach. And such a beamformer can be a fixed independent of the signals, or adaptive one, like this Frost beamformer or linearly constrained minimum variance beamformer, the LCMV. Basically, this is a counterpart of this Kaplan beamformer in the narrowband case. Okay, and we can also have this so-called generalized setup counselor, so GSC, which is also for wideband beamforming, wideband adaptive beamforming. Okay, or we can decompose the received signals into different frequencies and apply the narrowband subspace-based estimation method through either incoherent or coherent combination or focusing, all their variations. So that's another set of solutions. And then we can also apply this so-called frequency invariant beamforming technique. Frequency invariant beamforming technique to transform the wideband model into a narrowband one. So after this transformation, you have a similar narrowband model. You can apply all the narrowband methods available to this new model, transformed model. So using this frequency invariant beamforming technique. Okay, that's unique to this wideband case. Another unique approach to wideband DOA estimation is through this time delay estimation. Okay, we estimate the time delay. And again, there are many methods available. So the basic idea of time delay estimation is, okay, the correlation between two different received sensor signals will reach a maximum when one of them is delayed by the right amount and matched to the other one. So if you have two signals and you delay the one of the signals, two sensor signals, right? You delay one of them bit by bit and calculate correlation. Then when they are matched, you get the maximum correlation, right? It's a peak. And we can also use a sparsity-based approach. So the sparsity-based approach for narrowband case can also be extended to the wideband one, okay, which is the focus of today's tutorial. And the next, I will give a review of the sparsity-based approach for underdetermined narrowband DOA estimation, so which will form the basis of the approach for the wideband case. So section 2, so review of sparsity-based underdetermined narrowband DOA estimation. So we have three subsections. So first is array model, and then sparsity-based DOA estimation with physical sensors, and sparsity-based DOA estimation with virtual sensors, and some simulation results. So basically, there are many methods available for sparsity-based DOA estimation, and you can classify them into different categories based on different criteria. And here I just give a few representative methods, and we can classify them. Okay, here my criteria is okay. So either based on physical sensors or virtual sensors, how they apply this sparsity-based approach. Some of them, they apply this approach to the physical sensors directly, some of them to the virtual sensors. Okay, so there's two categories based on this criterion. Okay, now the model. So here, okay, assume we have n sensors. Okay, so in the previous part we said it's m sensors, but here we assume we have n sensors. So they are located at this alpha 0D, alpha 1D, and alpha n minus 1D. Okay, it's basically a linear array. And alpha 0, they are integer numbers. And D is a unit spacing. So alpha and D is the position of the nth sensor. And again, we assume there are k source signals, and we assume they are mutually uncorrelated. Okay, mutually uncorrelated. They are far-field. Actually, this assumption, okay, mutually uncorrelated, this assumption is not needed for the sparsity-based method with physical sensors. So for the virtual sensors, we have to make this assumption, okay? But for the physical sensor-based approach, we don't need this assumption. They can be correlated. They can still do effective DOA estimation, okay? And after sampling with the frequency FS, then we have this discrete form of this data model. So we use xi to represent the observed discrete signal vector. So this is a narrowband model. So xi and si n bar I, that's noise, as si is a source. So, and this I is this time index. Okay. Then the steering, this A theta is a steering matrix. It has dimension of this n times k, big N times big K. And each column is a steering vector. And this is a standard steering vector. So if we choose alpha 0 being 0, then basically we use sensor 0 as a reference. Then you see here it will be 1, the standard steering vector. Okay. And this lambda is signal wavelength. And for each snapshot, so basically one snapshot. So the sparsity-based approach, a big advantage of this sparsity-based approach is, okay, we only need one snapshot. So if just one snapshot will give you a good result. Certainly if you have more, then that will be even better, okay? But for one snapshot, okay, the approach is, okay, we construct this over complete dictionary based steering matrix. Okay, we generate this search grid of kg, so very big value, big to kg is much larger than this k. Potential incident angles, okay, you have a kg of them. For this linear array, so it can be from minus 90 degrees to 90 degrees, right? Or if you know the signal, the range of directions of the signal already, like from minus 6 degrees and then plus 6 degrees, 60 degrees, then you can generate those grades, okay, within that range, okay. Not the full range from minus 90 to 90. So it's an overall complete representation of this A theta. So I have this A theta G. And this A theta G is independent of the actual source direction theta K. So you don't need to know the direction of the source, okay. this G0, G1, and so on, they are created by the user, so they are not dependent on the actual source direction. Okay, so you create this very large dictionary, okay, large string matrix, and then you also create the corresponding source vector as GI. So suppose you have this kg, big kg is 1,000. You have 10 sensors, will be 10. This A set G will be 10 times 1,000. And then you generate this source vector as GI. This also is 1,000 times 1. Then you got this model. Certainly, also, although it's 1,000, right? Maybe you have 5 signals coming, then only 5 potential entries. 5 entries of this will be non-zero. Okay, ideally, if you can find the real locations, then only 5 of them will be non-zero. 5 entries of this SG. But now we don't know. Okay, we don't know. So this is a model. Then the idea is, okay, we minimize this SGI. The L0 norm basically is the number of non-zero valued entries. If you have 5 signals coming, then although the dimension is 1,000 times 1, actually only 5 of them are non-zero valued. So you minimize the number of non-zero valued elements. Subject to what? Subject this reconstruction error. So given this observed signal, this reconstruction error is smaller than a very small threshold value epsilon. Okay. And because of difficulty in solving this L0 norm based problem, so we use L1 norm as an approximation. Okay, so basically using L1 norm. So this is the standard formulation for sparsity based approach for single snapshot. Okay. And then you can solve this problem using many convex optimization toolboxes available. Okay, and this so you can draw after this running this optimization, you get the result for this SGI. Then you can draw this squared value of this SGI, and then the peaks will represent the corresponding source directions, okay, the real source directions. And different from L0 norm, which uniformly penalize all non-zero valued coefficients, right? The L1 norm is different. So if you have a larger value in this, then it will reduce that value more. So this L1 norm is only an approximation. To have a better approximation to this L0 norm, so you can use the method called reveated, okay, a reveated L1 norm minimization, okay, a reveated approach. Basically, for iterative process. So for each round, suppose after one round, you got the result as GI, then you find the values of GI. If you have a larger value, then you have a small coefficient weighting. You have a smaller value in this SGI, you have a larger weighting. And then you run this, with this new set of weightings, you run this optimization again until you reach a steady state with no, so after iteration, you have reached a steady state and then you can stop, okay? So this will give you a better result in general. So it's called reveated L1 norm minimization. And this L1 norm, this reveated one can be applied to all L1 norm based formulations. So it's a general approach. And when multiple data snapshots are available, so not just a single snapshot, and we could perform DOA estimation for each snapshot separately. But a more effective approach is to jointly estimate the DOA of impinging signals across multiple snapshots, employing the group sparsity concept, since they all have the same spatial support. Okay, basically, we calculate the so-called L21 norm. L21 norm. So, like you have P snapshots. So P is the number of snapshots. You have this new model is a matrix, the data matrix, source matrix. This is steering matrix, and this is noise matrix. and you can calculate the row vector. So you find the row vector. So this is the data source matrix. You can find the row vector, calculate the L2 norm of this row vector, and put the L2 norm into a new vector, this S height G. This new vector, you can minimize the L1 norm of this new vector. So this is the basically this is the L21 norm of this this SG. Okay. So this SG, okay, you construct the this large. So this SG corresponds to this S. Okay, like this small this small SG corresponding to this small s. Okay. Now you use this L21 norm to do this minimization. Okay, that's a group sparsity based approach. However, when you have a large number of source signals, let's say like 1,000. So you have A theta, you know, here this A theta G. A theta G, the dimension, suppose you have 10 sensors and you sample the angle range with 1,000 points. Okay, then it will be 10 times 1,000. And if SG you have 1,000 samples, then SG will be 1,000 times 1,000, will be large, very large value. Okay, this number of parameters. Okay, to optimize will be huge. Okay, then it will take a very, very long time. It's not efficient. So to reduce the complexity, we can perform singular value decomposition to this X, and project the data to a lower dimension signal space, and leading to the so-called L1 SVD method. Okay, and you can find details in this reference 8. Or another choice, another solution is okay to reduce the complexity is okay. It's called L1 SRACV method, sparse representation of array covariance vectors method, in this reference 28. So in this method, because we have a large number of snapshots available, so you can calculate the covariance matrix. You have a good estimation of the covariance matrix of the data, so which is given by this. This is a standard result, right? And then this second step is okay. You use A theta. You keep A theta. That's a steering matrix of physical array, right? And then you replace this part by this unknown, matrix P. That's a new source data matrix, P. And this P is much smaller dimension, right? You have n sensors, P will be n times n. Sorry, it will be k times n. Okay, k times n. So big K times big N. So this is in this case, you have a new model, like multiple snapshot model, right? This is the received data. This is the physical, the steering matrix of physical array, and this is the source, and this is the noise. Then you can apply the group sparsity based approach to this data model directly. Okay, that's this L1 SRACV method to reduce this complexity. So this method all based on the physical sensor, the steering matrix of the physical sensor, right? Physical sensor array. So far all the solutions are based on introduced here are based on the steering matrix of the physical array directly. And actually virtual arrays can be generated by exploiting the difference coarray concept for underdetermined DOA estimation. So it is difference coarray concept. What's the difference coarray concept? Okay, so consider this linear array with this set of this S. So S alpha 0D, alpha 1D, alpha 2D, and so on with that set of locations, the linear array. Then the second order difference coarray set is defined as this. Basically, you take the difference between this alpha n1 and alpha n2. n1, n2 is within the range from 0 to big N minus 1. So basically, you find the difference between alpha 0, alpha 1, alpha 0, alpha 2, alpha 0, alpha 3, or alpha 1 to alpha 2, alpha 1 to alpha 3, alpha 1 to alpha 4, and so on. find all the differences, right? And that will give you this set, second order difference covariance set. And then the legs in this set represent virtual sensors in a virtual linear array, and the significantly increased degrees of freedom can be exploited by various DOA estimation methods. Okay, so how can we generate this then? The question is, how can we generate this new set of legs or this new array, virtual array? Okay, then the idea is, okay, we find the covariance matrix. So in this case, we assume the signals, they are not correlated. Okay, then you have this result. Again, this is a standard result for uncorrelated sources. And then the next step is, okay, is we vectorize this RXX. If you do the vectorization, then you get a new model. So this A tilde theta, this is a new steering matrix. And this A tilde theta 1, theta 2, and so on, this is the corresponding virtual steering vector. And it's given by this A conjugate theta k, this Kronecker product A theta k. Okay. So, and this S tilde, they are the source powers. So sigma 1 squared, sigma 2 squared, and so on. And here, this one is obtained by vectorizing this identity matrix. So this is the new signal model. It's like you have one single snapshot, right? So here, because this Kronecker product is operation, you can generate this new steering vector, right? It has all the legs contained in this set, So second order difference covariance set. So in this virtual array model, the number of virtual sensors corresponding to the difference covariance is much more than that of physical sensors, and the equivalent source signals share the same spatial sparsity with the original impinging signals. So you still have the same, for this new array, the number of source signals is still the same, right? It's big K of them. And the increased DOFs, the degrees of freedom, are only available in the signal and noise power domain and can be exploited for underdetermined DOA estimation from the perspective of difference covariance concept. So you can modify this a little bit. So form this a new steering matrix. Basically, add an extra column vector to represent noise. Consider noise as an unknown variable. So a new source vector with noise included. So this is a single snapshot model, right? Single snapshot array model. And then you can construct this, okay, use its KG search grade, okay, KG, big value of KG, right? And then you construct n squared times KG matrix. This new steering matrix, okay, is overall complete virtual steering matrix. And then we have this new one, add the noise part. And then you have this single snapshot formulation, right? And here, this you do the optimization, you can find the first KG elements of this with the corresponding DOA results. Okay. And certainly, given this single snapshot array model, you can use, we call it spatial smoothing based music method. Okay, so it's a single snapshot because this is a vector and you got coherent sources, right? Because you have only one single snapshot. The sources, they are coherent. So you can use spatial smoothing and then apply a music algorithm to do this, to do DOA estimation. But here we're just we are focused on this sparsity-based solution. So we construct this overall complete this dictionary, this virtual steering matrix, and then using sparsity-based formulation to find the DOA results. So to avoid estimating the noise power in the formulation and reduce the computational complexity, we could remove the zero lag values of the covariance matrix and also merge those entries with the same lag. Okay, We'll talk about in detail this in a little bit detail in section 3. Okay. And to explore the advantages provided by different co-array, various sparse array structures have been proposed, such as nested arrays and the co-prime arrays. And the co-array concept can be extended to the case with a mixture of circular and non-circular signals. And so the pseudo covariance matrix of the array data is not 0 for non-circular signals. So you don't just calculate the normal covariance matrix and then do the vectorization. You can calculate the pseudo covariance matrix. Okay, this one, because for non-circular signals, this one is not 0, and then you can vectorize this. So you have more degrees of freedom. So as a result, for such a case, both sum co-array and difference co-array can be constructed to form a much larger virtual array to provide even more degrees of freedom. So because this one is a sum array, we generate a sum array, and this one gives you the difference co-array, right? So that's why you have both sum and difference co-array for these non-circular signals. So you can have a mixture of circular and non-circular signals and increase the degrees of freedom by generating the sum and difference co-array. Okay, and also if the signals they are not stationary, then you can create this so-called fourth order difference co-array. Okay, and for non-Gaussian signals, you can also construct fourth order co-array using like cumulants. Okay, so basically for the co-array for different order, so second order or fourth order, you can generate different co-arrays, and for higher order co-arrays, certainly you have more degrees of freedom. As I said, there are many different sparsity-based solutions available. So here I just give you some of them which are used often in literature. Here are some simulation results. We consider this uniform linear array with 5 sensors and also a minimum redundancy array, MRA, with the same number of sensors, but the locations will be different. It's a sparse array. And the unit spacing D is half lambda. Okay, and we have 2 sources from 10 degrees, -10 degrees, 10 degrees. And here we use different method. Okay, so here is for a single snapshot. So you have an error, right? If you have only single snapshot, certainly the estimation is not good, not that good for some cases. Okay, and then you have this. If you use group sparsity-based method for multiple snapshots, the result is much better. Basically, you have more information, right? Certainly, you should have a better result. And then here you have this L1 SVD method. So basically low complexity, and then you have this method. So all of them can identify the directions of the sources successfully. Okay. Here you can use MRA. You can also identify these 2 sources, no problem. And even more, so for the MRA is a sparse array, you can use co-array concept. You can estimate more sources. So here we increase the source number to 8. So you have 5 sensors, you have 8 sources, then this traditional formulation, you will not be able to identify them, right? But for this co-array-based method, you can still identify them successfully, okay? Another simulation, so with 2 sources, and you compare them with 1,000 snapshots, and you give different SNR values, signal noise ratio. You draw this root mean square error results. You find out, okay, because it's overdetermined, right? So all the methods, URA, MRA, they all work, right? But you see one interesting observation is, okay, for this URA, right, you increase the SNR, the estimation accuracy will improve further, keep improving, right? But for the co-array-based method, there you will reach a threshold, okay? Reach some level, then flat, stay flat. So it will not change anymore. You increase this SNR further, it will not increase correspondingly, okay? But for this low SNR stage, because of the large number of degrees of freedom available for this query, then the estimation result is much better than the traditional so uniform linear array based results. So that's actually this kind of performance behavior, okay? After you increase this SNR to some level, the estimation accuracy will stay the same. This one can be verified by the CRB results. Okay. Here is a RMSE results with respect to the number of snapshots. We fix dB, 0 dB SNR. So increase it, certainly get better, right? And also this query based gives you the best result, 0 dB, because it's like here, right? This MRA based is better than these two methods. Okay. So that's the sparsity based method for narrowband case. So section 3 will be underdetermined wideband DOA estimation with direct group sparsity. So that this will be in the second recording of this tutorial.